The triangle inequality is famous not just in geometry, but across all mathematics, and you'll see it in various forms. But the triangle inequality really does relate to a triangle. And the idea is that if you have an arbitrary triangle, then its longest side, the length of its longest side, is still less than the sum of the lengths of the other two sides. So here's what we want to show, right? So in this triangle AC, where the segment AC is the longest side, right, we want to show that the length from A to B plus the length from B to C is longer than the length from A to C, the distance from A to C. So we'll begin our proof by letting an arbitrary triangle exist, and we're just going to label its longest side AC. It doesn't matter which side is its longest side. It doesn't matter if it's isosceles. We'll just choose one of its longest sides, and that will work. And just to point out that if we'd picked any other side, we're done already. If AC isn't the longest side, right, then either this one is longer or this one is. So the inequality is trivially true if we don't pick the longest side. So here's one of those. This is why I'm doing the proof rather than you guys. It's one of those proofs where you have to kind of understand the construction. And we're going to use the isosceles triangle theorem here. So what's the idea? We are going to extend the line AB, right? And by the way, you can do it as well with CB, so it's sort of without loss of generality here. But we're going to pick one of the sides that's not the longest. We're going to extend it. We're going to make sure that the part we extend has the exact same length as this segment does. All right. And again, we're allowed to do that by the ruler postulate. I can create the line AB that goes through this whole, that goes here, and then I'm choosing by the ruler postulate to put D exactly R units from B. Well, what's R units? Well, R units is from the distance postulate. The distance postulate says that B and C, there's a real number that corresponds to the distance between B and C. So I'm using the distance postulate to get that measure and the ruler postulate to place D on here exactly R units from B. Okay, and you can see that we're going to end up with an isosceles triangle here. And because it's isosceles, we will get that these angles are congruent. And you can see I didn't put congruent, I said the measure of the two angles is the same. All right. So now look what we're doing. So we are trying to prove that the distance AB plus BC is greater than AC, but we don't have that, right? This is AB plus BC. The whole point though was if I create a segment AD with BD equal to this length, right, then the segment AD has exactly this length, right? So I'm basically making a segment AD that's exactly equal to the left-hand side that I'm trying to prove. And it should be clear why I'm going to use substitution here when I get this going on, but right now I'm going to use Theorem 10. So this is the point where I say that I mistakenly put Theorem 10 too late. I'm using Theorem 10 to prove what's in the notes, Theorem 6. When you're not, and we're not allowed to do that, but I could have put it earlier. And anyway, I'm going to use it because that's the only thing I have right now that gets me something like one length is longer than another. And what's Theorem 10? Theorem 10 says that in a scaling triangle, the largest angle is across from the largest side, and the angle with the smallest measure is across from the side, is opposite the side with the smallest length, the least distance between its endpoints. Okay, so, well, if that's true, I'm going to look at this big triangle. I'm going to say, hey, I know that AC is my longest side, right? And so, I mean, that was part of the given. So what am I going to do? Well, look. So we're looking at the angle ACD, right, which is this angle. And we know that that angle is bigger than BCD, right? Why? Well, because they both share the rays CD, and then B, right, is interior, right? I can pick an interior point to AD, and I know it's interior because it's on a line segment that has endpoints on these two rays of ACD. So since this angle BCD is, since this point here, call it P or whatever, since point P, oh wait, point B is what we said, right? Since B is interior to AD, then we know that this angle is smaller, right? That's the angle addition postulate. Okay. Well, what does it mean that this one is smaller? Well, nothing, but the fact that it is equal in measure to this other angle, that helps us. Now I have this angle ADC, and I have this angle ACB, and I know that ACB has to be longer. Therefore, the side across from it is longer than the side across from this smaller angle. Okay, so what do I know? I know that that AD, side AD is longer than side AC in the big triangle. Well, now I just get to use substitution, right? Because I have what I need as long as I know what AD is equal to, right? We know what AD is equal to right here. So I can substitute in the right-hand side. And that's where I'm getting this A, B, C, D just by substitution. And that is what we wanted to show. So we are done with the proof.